particularly on aggregation of heavy fractions, asphaltings and resins, using coarse-grained simulations, namely dissipated particle dynamics. Well, the work is very comprehensive, we'll listen to her and then ask questions. If something is really unclear, you can interrupt, but it is better, of course, if we.
Thank you. Good afternoon. My name is Neimark. My thesis of modeling of aspartame aggregation in crude oil by dissipative particle dynamics. So I will start with introduction. So aspartame is one kind of oil fraction, and the most common definition of aspartame is that it is soluble in toluene but insoluble in paraffinic solvents. And the structure of aspartame surely contains polyaromatic compounds, aliphatic set chains, and heterofunction groups. So simply judging from the structure, the aspartame can be divided into two kinds. One is called continental aspartame that contains only one polyaromatic compounds, and another is called archipelago aspartame that contains more than two polyaromatic compounds. And the molecular weight of aspartames can range from a few hundreds to thousands of solvents, and hydrogen to carbon ratios are usually close to 1. And the elements compositions of aspartame from different oil sources are generally in a good consensus. So next is crude oil. Crude oil is a mixture of saturates, aromatics, resins, and aspartames. So the importance to study the aspartame aggregation is that aspartame is a dominant component that caused many industrial problems in crude oil. And as research currently existed literatures that studied using DD models to study the aspartame aggregation, we summarize two problems. One is that a few DD models of aspartames have a rough similarity to the real geometric structures of aspartames, and this is because that the researchers simply cross-grained the DBDBs out of the structure by fraction and displays the volume differences. For example, one polyaromatic compound would be considered as 1 dBdBs, and by doing so in folding simulations, the packing structure of aspartames would disappear. And another problem is that most of the simulations are lacking systematic parameterizations. So the parameters in those studies are either assigned arbitrarily or taken close to the simulations for surfactant in water. But however, the behavior of oil system is subtle in reality. So we want to build a model that use different beads or diameter for DBD, and that can well represent the geometric structures of aspartames, and also provided parameter methods that could reproduce those subtle behavior. And since the aspartames precipitation could take months to accomplish the final equilibrium, and but before the phase separating, there would be various colloidal structures of aspartames. So we mainly focus on those colloidal structures. The simulations here is a dissipative particle dynamics. So in DPD method, a molecule is divided into beads, and the interactions between beads are governed by the Lagrange equation of motion. And the force contains conservative repulsion force, and random force, and drag force. So besides those three forces, we also introduced the bond and angle force. And these forces are supposed to regulate the geometry of the molecules. So the next session is to decide the DPD models of essential components that used to model the crude oil. So firstly is for solvents. So we take the hexane to represent the saturates, and toluene to represent the small aromatic hydrocarbons in crude oil. The RC and the intra-component repulsions can be obtained from Groth-Vary equation, but Groth-Vary equation is only suitable for single component system. So the the density and the compressibility. So in binary system with two components, that the density and the compressibility of each kinds cannot be fit at the same simulation box. So to avoid the strong deviation of density and to maintain the pressure means the mechanical equilibrium. So we decided that the toluene beads here would share the same RC and repulsion parameters as the hexane beads. And by calculating the effective volume, we here decide one hexane bead would be one hexane molecule, and one toluene bead would be 115 toluene molecule. So the next component is polyaromatic course. The polyaromatic course would be used for later modeling both aspartanes and resins. So three standards must be satisfied. First, it should be a flat geometry. Secondly, it has a surface density that is equal to that of the graphene sheet. And thirdly, the simulated layer distance should have a good agreement with the experimental distance of the stacks. So since the typical polyaromatic course in aspartame usually contains a few aromatic rings. So here we decided each ring would represent one DPD beads. And here shows two examples. One is a pairing that contains four aromatic co-beads, and another is called a 14-mer that contains 14 aromatic co-beads. And here we introduced angle stiffness for about 40 to 45 this flat geometry. And the surface density here we calculated for both graphene sheets and the pairing. The graphene sheet and the polyaromatic course models are quite equal to each other. The next step is to fit the intra-component repulsions and the RC. So to do this, we build a series of models for benzene, naphthalene, and pairing and 14-mers. And then we perform the simulations with different combinations of intra-components repulsion and RC. And then we try to find the best match that has a simulated density equal to the real density, and decent effective volume ratios between those models, and also the layer distance of the 40-mers that is in the range of the literature records for the stack distance. And for the distance of a layer, we use the RDF analysis to get the layer distance between those locally packed structures. So now we have two kinds of models. One is for solvents and another is for polyaromatic compounds. So now we decided the interactions between them. Since aspartame generally has a solubility definition that is insoluble in hexane, but has a reasonable solubility in toluene for about several percentage. And there's limited literature records about the aspartame solubility. So here we decided to use reference compound pairing to reproduce those interactions. Because the hexane pairing, the solubility of hexane pairing is about 99%, and the toluene is the solubility of toluene is about 90%. So we think those can simulate the subtle behavior of the aspartames. So to to figure out the interactions between them, we started a few simulations that has increasing repulsion parameters from 57 to 68, and each simulations are started with an initial configuration that half of the box is filled with pairing and the other half is filled with solvents. The corresponding densities and solubilities for each component can be obtained from the density profile. And here we found that 65 would be the optimal parameters to describe the interactions between the polyaromatic clause and the hexane. And we also estimated 58 from the linear dependence of logarithm solubility on delta A to be the interaction parameters between polyaromatic clause and the toluene. So the third DPD model here is aliphatic hydrocarbons. So if we recall earlier that we already discussed the DPD model about hexane, but here the reason that we cannot use that solvent hexane to describe the set chain is because it's because if we use that hexane model to attach to the polyaromatic clause, usually aspartame set chains contains about 5 to 6 carbons in one set chain. So it means there would be only one big DPD base to represent the set chain. But however, the aggregation of aspartames is like quasi-scalar, and those set chains in the aspartames acts like some soluble tails for the micelle. So we think, we thought that we still need some smaller DPDBs to represent the length feature of these set chains. So as we already have a hexadecane model from a previous work in the same group, where the basic concept is that each two carbon atoms would be considered as one DPD. So here the intra-component repulsions were fitted to the density of the liquid hexane, and so we have to notice that here the angle stiffness cannot be as strong as the angle stiffness that we used to fortify the polyaromatic compounds, because the carbon bonds has a nature to either rotate or vibrate. So we simulated a few simulations that has increasing angle stiffness from 0 to 40, and compared the corresponding distance distributions to the results from a molecular dynamic, and found that 2.5 would be the optimal match that will describe the behavior of the carbon set chains. So the last component is the heterofunction group. So heterofunction group usually in aspartames would serve as some hydrogen bond donor. So here we introduced a hydrophilic component that is described as one DPD, and the parameters between itself and two other beads are fitted by the modified mixing rules. So in summary, we have 5 kinds of beads. Hexane beads and toluene beads would be solvents, and hexane beads represent the saturates, toluene bead would represent the aromatics, and the pairing beads here would be used later to build the polyaromatic clause for aspartames and resins. And the aliphatic bead would be used to build the set chains for both aspartames and resins, and heterofunctioning group beads. And the corresponding parameters are displayed here in table 6. Next, we build the aspartame models. The first model that we built is a small single core aspartames, here called S aspartames. This aspartame has only one this aspartame has only one aromatic center and attached with 3 side chains. So the molecular weight of this small aspartame is quite light. It's about only 800. So we also consider the archipelago aspartames that contains 3 polyaromatic cores, and each of the cores are connected with side chains to make a loop. And we add 5 extra side chains to the peripheral of the cores to make the hydrogen to carbon ratio equal to 1. So besides the small single core aspartame and the large multiple core aspartames, we also consider the possibility of large single core aspartame. So here we build the third aspartame. It's called air aspartame that has a big single polyaromatic core in the center and attached with several side chains. And we also build a resin model that has a small aromatic cores and a long side chain. To validate our aspartame models, we try to reproduce the dilution experiments. The specific details for the simulation is that we initiate a simulation box for about 20 by 20 by 60, and each of the simulations are started with the initial configuration that one end of the box is filled with the small aspartames, and for the rest of the box is filled with the solvents that have different column to hexane ratio. And we also reproduce the mixtures of aspartames that has both archipelago and small aspartames in it to reproduce those dilution experiments. And after the simulation reached the equilibrium, we calculate the average of the concentration for each simulations and obtain the concentration data to compare with the experimental dilution results of aspartames. So here, CSB6HO and H are aspartames from a different oil source, and by comparison, we found that the agreements between the simulations and the experiments are quite acceptable, despite that there would be 1.5 to 3 times differences. And the reasons for this deviation could be various. So now we study the aspartame aggregation pattern. We first start with the small aspartames, and the simulations is start with 5% of small aspartames in the box that has solvents with different tolerance to hexane ratio and different proportion of resins. So the final configuration are displayed here. So if we take a look at the figure A, we can find that small aspartames are existing in the system either in a single form or from some small stacks. And the stack's size can be drastically increased if the solvent is pure hexane. And by adding 5% of resins to the system, the size of the stacks are somehow lightly changed, and the system become more dispersed. So by adding 20% of resin to the system, we can see that even in pure hexane solvents, the small aspartames are soluble. So as we studied the size distribution of those simulations, and we found that by replacing half of the tolerance by hexane, the free small aspartames in the system could be decreasing from 74 to 44, and accordingly the average aggregate size can increase from 4 to 5. And the distribution pattern here shows that some big aggregates can exist in tolerance when resin is not involved. And the reason here can serve actually serves like a surfactant that can increase the diversity. And here shows one example of the simulations that shows the position of the aspartame course and the resin course. So it can be observed that some of the resin cores are attached on the surface of the aspartame stacks. So next we simulated the aggregation pattern for the archipelago aspartames. So here the archipelago aspartames coexist with the small aspartames, and we put 2.5 archipelago aspartames and 2.5 percentage small aspartames in the simulation box that have a different tolerant to hexane solvent ratio solvents, and the resins here would have different proportion. So different from the pattern for the small aspartames, archipelago aspartames here can form really big aggregates, and it shows strong trains to aggregates, and so when the resin is absent, the archipelago the single from archipelago aspartames is sporadically found in the system. So by adding small amount of resin to the system, the archipelago's pattern can slightly change, and only by adding large sufficient amount of resins to the system, the aggregations can be disturbed and the solution become more dispersed. So here shows the size distribution for both archipelagos and small aspartames in this system. The left three is the size distribution of archipelago aspartames in the order of with no resin, with 5% resin, with 20% resin. So for the first pattern, we observed that the average number of archipelago aspartames in an aggregate can be really big, and by adding 5% of resin, so the average number of molecules in an aggregate can be decreased to a certain extent, and by adding 20% of resins, the aggregation, the number of molecules in one aggregate can drastically decrease. And the right three patterns shows the size distribution of the small aspartames, and the small aspartames aggregates number can the number of small aspartames in an aggregate are regulated by both the tolerant to hexane ratio and the portion of the resin. So we also try to learn the shape of the aggregates. So here we use the asymmetry factor distributions. So asymmetry factor is defined as a ratio of the radius of gyration of an aggregate to the imaginary radius of gyration to a spherical shape that has the same amount of beads. So if this asymmetry factor is close to 1, it means this aggregate has a shape that it can be considered as a sphere. So we found that in all 9 simulations that the asymmetry factors are all closer to 1. So that means regardless of the size of the aggregates, all simulations has the spherical aggregates in the system. So the last aggregation pattern we learned is called the large single core aspartames. Here, since we found that the large aspartames can the aggregation pattern of the large aspartames can hardly be affected by the tolerant to hexane ratio, so we eliminated the results for the simulations intolerant and the simulations intolerant to hexane mixtures, and we only represent the simulations for the large aspartame in hexane with different portion of resins. So from the final configuration, it can be found that the large aspartames can form some crystal structures, and the stacks they are forming are highly organized, and this can even be considered as some crystal. So we also present the asymmetry size, asymmetry factor distribution here, and from that when there is no resin in the system, the asymmetry factor can be as large as about 8. That means the structuring of these aggregates is elongated and is not spherical. So in conclusion, this study is the first attempt that used a different DPD bezel diameter to describe the complex system. The reason that we're doing so is because polyaromatic compounds are both light and thin, so we think that the smaller DPDBs could be better to represent their geometric differences. And during the modeling process of the components for the crude oil, the geometry of the molecules are determined by both covalent bonds and angles, and the intercomponent parameters are determined by using some reference compounds such as pyrene and hexadecane to fit the properties like densities and mole fractions. So by doing so, this can represent a good test for parameterizations for complicated molecules, because all the components in our studies is highly strong hydrophobic components. So that means if we use a conventional DPD model methods, those components would be simply considered as one type of DPDBs. So the outcome of our models shows that we have reproduced the reasonable pictures of aspartame segregation, and especially the dilution simulations has a good agreement with the experimental data. So at the end, I would like to thank my advisor, Dr. Vishnapu, and Professor Neimark and Professor Dutt as my committee member, and all my research group members. And thank you all for coming today.
Okay, we'll start. We'll welcome questions from the audience first.
What is the resin?
Resin?
Just show this.
What? You mean the resin?
Yeah, what you mentioned that you use the resin, but what is it specifically in the system?
Yeah. So resin is
I see.
Yeah, it's another kind of oil fraction, and the basic feature of resin is that it has a long sections, usually longer than the sections that we found in aspartames, and the aromatic cost of the resins is usually smaller than those big polyaromatic costs that in aspartames.
Well, on the technical side, if you first add heptane to the system and deasphalt the system, so asphalt and so on, then you can add hot pentane to the system, and then the resins start forming. So it is just basically smaller polyaromatic compounds.
So, if I can have a follow-up, what recommendations would you give an experimentalist based on your work? Yeah, so you have.
All the experimental application study of the aspartame.
Yeah, so you said this is a problem in industry. What would you recommend to them?
Yeah, so I think the study here is just for the theoretical, and for the specific steps to improve the industrial process, it may need more considerations, and yeah.
So your asymmetric factor is somehow related to the fractal nature of matrix.
Symmetry factor?
The asymmetric factor you talked about.
Yes.
Is there any relation to fractal dimension, fractal nature of the matrix?
Fractal dimension?
Yeah.
So first of all, I don't know what is a fractal dimension.
So your aromatic cores some angle potential, so how do you actually make it a particular orientation? Aromatic core. So how
Aromatic
you,
cores? Yeah. So you mean the aromatic cores for last buttons? Like that?
yeah, you introduce some angle potential or something?
Oh yes, angle potential.
That's
Yeah.
right.
It's here. So we only use the 180 degrees of angle potentials to fortify the and the angle stiffness for 40. So this structure can be flat and thinner and yeah.
So, looking at the experiment, or looking at the compositions that you looked at, how did those compare broadly with things that are found in nature with asphaltene compositions? So, like, are these reasonable ranges to be looking at?
Yeah,
Yeah.
yeah, I think so. Yeah.
Okay.
Yeah, I would say that, of course, the different oils contain very different ranges, like from 1% and then all the way up to 20 or something like this. But 5%, if you look at experimental, basically, data for asphaltene dilution that people work with, so this is so this several percent is what people typically work with on experiment.
And they find similar behavior with the aggregation based on this?
Oh, okay, so, Tamim, could you respond?
So experimentally, do they find similar aggregation patterns to what you found based on the compositions that you used?
Yes, because there is some cornerstone models that is called a Young model and Young and Morin modified. There's some cornerstone models for these asphaltens, and those asphalten patterns is that described as some small fused rings that parallel packing on each other, and those small clusters then aggregates to make big clusters, and those is a basic patterns for these aggregations.
Yes. Do you observe this stacking of these island, like these layers, in your
Yes.
simulations?
Yeah, here just shows one example of the floating Morse, and I make it a rotation pattern so that we can see some locally packed structure. And here both red and yellow bits are the floating Morse. So I just make them.
Yeah, I think the question was about the behavior in solids, not pure for photonics.
Yeah, actually we observe those parallel packing structures, but it's just because here these are too small to be seen.
Mm-hmm.
Basically, all small micelles are parallel pack structure with micelle size like 1 2 nanometers. So, as actually they are an experiment, because even it is said that they are soluble in toluene, but in fact this solution is not really just urine.
Okay.
Any questions?
Okay, so if there is no questions from the audience, so right now only we remain, right?
Yeah.
Yeah, so then the general audience can